Welcome to the DIY Honda Garage channel. The DTC, or Diagnostic Trouble Code P16E3, indicates a communication error with the battery sensor LIN, Local Interconnect Network, on the Honda CRV models from 2017 to 2022. This error points to issues within the powertrain control module, PCM, or problems in the wiring and connectors that lead to the battery sensor. The PGM-FI, which stands for the Programmed Fuel Injection System, uses the battery sensor to monitor the vehicle's electrical system. The battery sensor is typically located near the negative terminal of the 12-volt battery, measuring voltage levels and communicating these readings to the PCM. A malfunction in this communication could lead to performance issues or decreased vehicle functionality, requiring thorough diagnostics to identify the source of the error. The PGM-FI-Battery sensor plays an essential role in managing the engine performance by monitoring the voltage levels in the vehicle's electrical system. It is situated close to the negative terminal of the 12-volt battery. By relaying this voltage data to the Powertrain Control Module, PCM, it helps ensure that the engine operates efficiently and that the electrical system functions correctly. Any discrepancies in this communication can result in the P16E3 error code. Additionally, this code may also relate to complications with the LIN communication line, which connects various components of the vehicle's electrical system to ensure they function in harmony. Therefore, understanding the battery sensor's role is crucial to diagnosing this issue accurately. Several potential causes for the DTC P16E3 include loose terminals on the battery sensor itself, which could interrupt communication between the sensor and the PCM. Poor connections within the surrounding wiring can also create similar issues, preventing accurate diagnostics. The battery sensor itself may be faulty, leading to unreliable voltage readings. Moreover, shorted LIN wiring can interfere with the communication line, effectively halting the signal from the battery sensor to the PCM. Identifying these causes is integral to rectifying the DTC P16E3 code, and effective troubleshooting must differentiate between these possibilities. When the DTC P16E3 is present, symptoms can include noticeable engine performance issues, such as decreased efficiency or rough idling. It's also common for the battery warning light to illuminate on the dashboard, indicating a fault in the battery system. Additionally, drivers may experience diminished electrical functionality in various systems of the vehicle, including accessories that rely on a stable voltage supply. Such symptoms not only alert the driver to a potential problem, but also serve as indicators that the vehicle's electrical system requires further examination to ensure everything is functioning optimally. The first step in troubleshooting DTC P16E3 involves verifying the existence of the problem. Begin by turning the vehicle to the on mode without starting the engine. Use the Honda Diagnostic System HDS tool to clear the DTC from the system. After clearing, switch the vehicle to off mode, ensuring that all electronics settle. Wait for approximately 60 seconds to allow the system to reset. Following this, turn the vehicle back to on mode and check for any pending or confirmed DTCs using the HDS. This diagnosis helps establish if the issue is persistent or intermittent, guiding subsequent troubleshooting efforts. In this step, you will need to check again for pending or confirmed DTCs using the HDS. Specifically, look for any indication of DTC P16E2, which refers to the AC generator LIN communication error. If P16E2 is indeed indicated, proceed directly to Step 5 for further investigation. If not, advance to Step 3. This step is critical as it narrows down potential issues by evaluating other LIN communication errors within the powertrain control module arrangement and helps clarify where the problem may lie. The third troubleshooting step requires checking for any pending or confirmed DTCs, again with the HDS, focusing on DTC P16E3, which pertains to the shutter grille LIN communication error. If this code appears, it implies that there is another potential source of communication failure that needs addressing. So move to step 9. If P16E3 does not show up, move on to step 17 to continue the diagnostic process. This step helps in identifying whether there are multiple LIN communication errors affecting the system, thus refining the diagnostic approach. Continuing the diagnostic process, the fourth step again involves checking for any pending or confirmed DTCs using the HDS, specifically for DTC P16E3, which indicates a LIN communication error related to the PCM's DC-DC converter. If this DTC is evident, follow through to step 13 for a more in-depth investigation into potential issues. If not, proceed to step 17 to carry on with the general troubleshooting. This step is crucial in isolating any potential failures in the LIN communication, directly impacting several vehicle systems reliant on consistent signaling. In this fifth step, the troubleshooting begins by turning the vehicle to the off or lock position to ensure safety during diagnostics. Disconnect the 12-volt battery sensor's 2P connector, preparing to measure the resistance between designated test points. The test condition mandates that the vehicle remains in the off mode with the battery sensor disconnected. The first test point will be the female terminal number 2 of the battery sensor, while the second will be a reliable body ground. If the resistance measures 1 megaohm or more, you will proceed to step 7. If not, this indicates a wiring issue or a short, and step 6 will need to be implemented. Step 6 focuses on identifying potential shorts within the LIN wiring. Begin by jumping the SCS line with the HDS to enable a thorough check and then wait more than 1 minute. This allows the system to stabilize. The next phase involves checking for continuity between terminal number 2 of the battery sensor's 2P connector and body ground, while systematically disconnecting connectors one at a time, including the alternator 1P connector, PCM connector A, and others specified. If the continuity ceases when disconnecting any one of these connectors, this indicates that the LIN wiring is acceptable, and the faulty part causing the problem should be replaced. If continuity persists, repair is necessary for a short in the LIN line. Or step 7. First, reconnect the 12-volt battery sensor's 2P connector to restore the electrical pathway. Then, disconnect the alternator's 1P connector to isolate it from the circuit. With the alternator disconnected, measure the resistance between the first test point, which is the female terminal number 1 of the alternator connector, and the second test point, which must be a solid body ground. If the measured resistance is 1 megaohm or more, you move on to step 8. Conversely, if it reads less than 1 megaohm, this indicates a malfunction in the battery sensor itself, warranting its replacement. In step 8, you again jump the SCS line with the HDS and wait for more than 1 minute. This step is followed by disconnecting both the 12-volt battery sensor's 2P connector and the PCM connector A. Resistance is then measured between the female terminal number 2 of the battery sensor connector and terminal number 10 of the PCM connector. Under these conditions, if the resistance is 1.0 ohms or less, this implies that the LIN wire is functioning as expected. You should then consult additional authorized service information or consider substituting the known good PCM if further issues arise. However, if resistance exceeds this value, repair and open in the leading wires between the PCM and the battery sensor. This ninth step begins with turning the vehicle back to off or lock mode and disconnecting the battery sensor's 2P connector again. Resistance is measured between the battery sensor connector's female terminals, number 2, and body ground. Ensure the vehicle remains in off mode during this assessment. A resistance reading of 1 megaohm or more suggests that further troubleshooting can continue to verify the wiring integrity. If resistance is less than this threshold, you must move to step 10, focusing on identifying shorts in the LIN communication. Step 10 involves further checks of potential shorts along the LIN wiring. Start by jumping the SCS line with the HDS again, waiting over a minute before proceeding. Next, examine continuity from the terminal number 2 of the 12-volt battery sensor's 2P connector to body ground. Disconnect connectors one at a time, including the PCM connector A and the others specified, while monitoring for any change in continuity. If the continuity disappears upon disconnecting one of the connectors, then there is nothing wrong with the LIN wiring. Replace the faulty component that caused the disconnection. Should continuity remain uninterrupted, this indicates a wiring short that must be repaired within the LIN system. In step 11, reconnect the 12-volt battery sensor's 2P connector and disconnect the shutter grille connector, either upper or lower. Measuring the resistance under these conditions will happen between female terminals number 3 of the shutter grille connector and body ground. Ensuring that the vehicle remains in the off state is essential to prevent any electrical mishap. If the resistance reading is 1 megaohm or more, you'll proceed to step 12 for additional checks. If not, this signals a malfunction within the battery sensor, necessitating its replacement. Step 12 follows a similar protocol to prior checks. You will once again jump the SCS line with the HDS, allowing for a wait period of over 1 minute. Disconnect both the 12-volt battery sensor's 2P connector and the PCM connector A during this phase. Measure the resistance between female terminal number 2 of the battery sensor and terminal number 10 of the PCM. A reading of 1.0 ohms or less confirms that the LIN wiring is operational. If this condition is met, examine any authoritative service documentation related to the DTC or symptoms encountered. Alternatively, consider substituting a known good PCM. If resistance measures higher, repair any breaks in the LIN wiring between the 2 points. In step 13, you begin by switching the vehicle to the off mode and disconnecting the battery sensor's 2P connector again. The resistance measurement should occur between female terminal number 2 of the battery sensor connector and body ground, ensuring the vehicle remains off during this test. As with earlier checks, if resistance is found to be 1 megaohm or more, there's no evident short, and you can proceed to step 15. If resistance is less than this, step 14 will be necessary to diagnose potential shorts within the LIN communication. In this step, you will utilize the HDS to jump the SCS line once more before checking for continuity along the LIN wiring. After jumping the SCS line, disconnect the battery sensor's 2P connector and measure continuity towards body ground. Avoiding shorts requires disconnecting other connectors, like the PCM and alternator, while checking to see if continuity is interrupted. If it goes away while one connector is unplugged, the wiring is in working condition. However, if continuity remains, you must rectify the short in the LIN wiring that may involve multiple components, including the battery sensor, alternator, and others in the circuit. Step 15 requires you to reconnect the battery sensor's 2P connector, followed by disconnecting the DC-DC converter's connector A. After this is complete, measure the resistance between female terminal number 1 of the DC-DC connector and body ground. Calibrating the vehicle's state to off is critical for safe measurements. If the resistance is found to be 1 milliohm or more, you will progress to step 16. However, if resistance reads lower, it indicates a malfunction in the battery sensor, leading to its necessary replacement. In the final troubleshooting step, jump the SCS line with the HDS and wait over 1 minute. Subsequently, disconnect the battery sensor's 2P connector in addition to the DC-DC converter's connector A. Measure the resistance between female terminal number 2 of the battery sensor and terminal number 10 of the PCM under these specific conditions. A reading of 1.0 ohms or lower indicates that the LIN wiring is intact. If this is true, investigate additional authorized service information regarding potential DTCs and symptoms. Should the resistance exceed this threshold, repair any open wiring along the path between the PCM and battery sensor. Once repairs related to DTC P16E3 have been completed, it's vital to confirm the effectiveness of these repairs. Begin by clearing all diagnostic trouble codes using the HDS. This step ensures that if the original issue was resolved, no new codes should appear in the system. Next, it's important to conduct a test drive of the vehicle to ensure it operates smoothly under typical driving conditions. Perform weekly checks and keep a close eye on the dashboard indicators to confirm that no warning lights return. If everything checks out, you can feel confident that the issue associated with DTC P16E3 has been thoroughly addressed, ultimately enhancing vehicle reliability. To mitigate the risk of encountering DTC P16E3 in the future, proactive maintenance is key. Begin with regular checks of the battery connections, ensuring that both positive and negative terminals are clean, secure, and free from corrosion. Inspect the wiring associated with the 12-volt battery sensor and other related components for any signs of wear or damage, as this can lead to communication failures. It is also advisable to use high-quality components for replacements and repairs, as inferior parts may lead to issues down the line. By adhering to these preventive measures, you will enhance the longevity and performance of your vehicle's electrical systems. In summary, the DTC P16E3 reflects a communication error tied to the vehicle's battery sensor and the powertrain control module. The troubleshooting process emphasizes a step-by-step approach aimed at isolating the problem, whether it be loose terminals, faulty components, or wiring issues. Diagnosing this issue involves checking multiple systems and connections to ensure accurate readings and reliable performance. By understanding the interconnections between the battery sensor, LIN network, and PCM, you'll be equipped to tackle any related issues effectively. Make routine maintenance a priority to prevent future occurrences, ensuring optimal vehicle functionality. Please like and subscribe to the channel. See you next time.